all. Now we'll continue the inequalities, different questions and solution. And the question is given in different examination. So I'll start the question number 4 now. The question is basically if ABC are positive real number, so R plus means set of all positive real number, and N is positive rational number, N belongs to Q plus positive rational number. So prove that a to the power n into a minus b into a minus c plus b to the power n b minus a b minus c plus c to the power n c minus a c minus b, that quantity always greater than equals to 0. So now we'll move to the solution. So what is exactly given? We have given two information. The first one is all ABC are positive real number, and second information is n is positive rational. What we have to prove? We have to prove that a to the power n a minus b into a minus c plus b to the power n b minus a multiple b minus c plus c to the power n c minus a multiple c minus b, this whole quantity is always greater than equals to 0. That we have to prove. So how we'll start the problem? We'll start the problem by using different cases. So first case 1. Here ABC are positive real number. There may be one case all ABC are equal. So let all ABC, A equals to B equals to C, they are equal. So in that case, then the left hand side of the given expression, that means a to the power n into a minus b into a minus c plus b to the power n into b minus a into b minus c plus c to the power n c minus a into c minus b, that value will be 0. Because here a equals to b, that means a minus b 0. A minus c is also 0. So this value is trivially 0. As since each term equals to 0. So this is case 1. Case 2, it may happen the two of ABC are equal. Let 2 of ABC be equal. So in that case, we can consider different subcases. As for example, we can consider A equals to B and that is not equals to C. We can consider B equals to C not equals to A. And we can consider C equals to B not equals to B. So these are the three subcases under case 2. But without loss of generality, we just consider A equals to B and both A and B are not equals to C. So just without loss of generality, we consider A equals to B, say, and it is not equals to C. So in this case, just observe the left hand side. So left hand side, that will be c to the power n multiple c minus a into c minus b. Why? Because a equals to b, that implies a minus b, this value will be 0, and hence we can call this value will be 0, and hence we can conclude these terms and this term, this is 0. So the remaining term will be c to the power n c minus a into c minus b. So here a equals to b, so we can write c to the power n c minus a multiple c minus a. So that means that will be c to the power n c minus a whole square. And that is strictly greater than 0. Why? Because c not equals to a, that implies c minus a, that whole square is greater than 0. And c is already given, c is a positive real number. And c belongs to R plus. This implies c is also greater than 0. And this implies c to the power n is always greater than 0 for all n belongs to q plus. See the second case, we see the left hand side expression. This big expression is always strictly greater than 0. Now I consider the third cases. All ABC are not equal. That means no two of ABC are equal. So this will be case 3. Here we consider no two of ABC are equal. So that means here we consider the case A not equals to B not equals to C. That is, we consider the case A not equals to B not equals to C. But we can arrange it in a order. So as for example here, without loss of generality, let we just consider A greater than B greater than C. Just to think this is a real line, and here the 0 is there. So we're just talking about the positive real numbers. So just here consider A is here and B is here and C is here. Because we just see the positive side, that means R plus portion. So let A greater than B greater than C, then we can write A minus B obviously greater than 0. B minus C, that part is also greater than 0. And A minus C, this is also greater than 0. From this we can write the expression, now A to the power n into A minus B into A minus C plus B to the power n into B minus A into B minus C. This expression we just take the common A minus B. So this will be A to the power n A minus C minus B to the power n B minus C. Now the case is, since A greater than B greater than C, so this implies A minus C greater than B minus C, this quantity greater than 0, and A greater than B greater than 0, that implies A to the power n greater than B to the power n, as n belongs to positive rational number. And hence using this inequality, we just put here, and that expression must be strictly greater than 0. So obviously also we have another term, this is c to the power n c minus a into c minus b. That quantity must be greater than 0 because c minus a is negative and c minus b is also negative. Why negative? Because a less than b less than c, and this implies if we multiply two negative numbers c minus a into c minus b, that quantity greater than 0. And C obviously a positive real numbers and n belongs to q plus, that implies C to the power n, that obviously must be greater than 0. So just we add this portion and this one, what we will get? A to the power n a minus b into a minus c plus b to the power n b minus a into b minus c plus c to the power n c minus a and c minus b is the whole term on the left hand side, that would be greater than. Just adding, this is the star and this will be double star, and here the since by star plus double star. Okay, so combining all the cases, what we conclude in the first case is this left hand side is equals to 0, second case is it is greater than 0, and third case is it also greater than 0. So we just conclude our conclusion, combining all the cases, we say that a to the power n into a minus b into a minus c plus b to the power n into b minus a into b minus c plus c to the power n into c minus a into c minus b, that portion must be greater than equals to 0. And obviously here you just see the equality holds. Equality holds only the first cases where a equals to b equals to c. In that case, this big expression is basically equals to 0. So this is proved. Now we'll just recall, we'll state one statement of Oster's inequality. So the question is, what is Oster's inequality? Oster's inequality. So just to recall the statement of Oster's inequality. So what is the statement? Statement is basically if a1, a2, a1, a2 dot an all are positive real numbers and all are less than 1. That means a1 less than 1, a2 less than 1 dot an less than 1, and Sn equals to sum of this n real positive real number a1 plus a2 plus dot an. Then we can conclude Roman 1, we can conclude the 1 minus S1, this is strictly less than 1 minus A1, 1 minus A2 dot 1 minus An, that product, and that less than 1 by 1 plus Sn. This is the first inequality. And second inequality, we can conclude 1 plus Sn, this is less than 1 plus A1, 1 plus A2, multiple 1 minus n, that quantity is less than 1 by 1 minus sum of this term 1 minus Sn. So this is very, very important, and we need to recall the inequality as it. So this inequality is basically called the Oster's inequality. So just based on this inequality, we have different problems, but I will just discuss one problem here. The problem is, next question, question number 5. This is if n is positive integer, that means n belongs to z plus, then prove that 1 multiple 3 multiple 7 multiple 2 to the power n minus 1 divided by 2 multiple 4 multiple 8 2 to the power n, this is always less than 2 to the power n by 2 to the power n plus 1 minus 1. We need to prove this inequality with the help of Oster's inequality. So how we'll prove it? We'll prove it just considering some n positive real numbers. So now just to see the inequality again, a1, a2, n are positive real numbers, all are less than 1. So just we consider here, we take, say, a1 equals to 1 by 2, a2 equals to 1 by 2 square, an equals to 1 by 2 to the power n. So our observation is that, observation is basically all ai is greater than 0 for all I equals to 1 to n. That means ai are positive real numbers for all I equals to 1 to n. This is the first observation. And second observation, what is our Sn? Sn equals to a1 plus a1 plus a2 plus an and that will be half plus half square plus dot 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 1 by 2 to the power n and into 1 plus half plus dot 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 1 by 2. So obviously this value will be, this implies 1 into 3 into 7 dot 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 2 to the power n minus 1 by 2 into 4 into 8 2 to the power n, that value less than 2 to the power n by 2 to the power n plus 1 minus 1. Now we'll move to the next question, next inequality. This is also very important. The inequality is named as a Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. First, we need to know about what is the exact statement of Cauchy-Schwarz inequality, and then we can prove some problem related to Cauchy-Schwarz inequality. So now we'll move to the statement first, just like Weierstrass inequality. Statement is if a1 a2 dot dot an and b1 b2 dot dot bn be all real numbers, then a1 square plus a2 square plus dot dot an square multiple b1 square b2 square plus dot dot bn square, this is greater than equal a1 b1 plus a2 b2 plus dot dot an bn, that whole square. Now the question is when equality occurs. So the equality occurs when, first Roman one, if all ai equals to 0, for all I equals to 1 to up to n, because if all ai equals to 0, this quantity will be 0, and this multiplication term on the right hand side, this is also will be 0. Or we can say the equality occurs if bi equals to 0, I equals to 1 to n, just to put the value of ai bi, you can see the equality. Or both ai equals to 0 and bi equals to 0 for all I equals to 1 to up to n. This is one case where we can say the equality occurs. And another case, if ai equals to some k bi. So you can write in that way ai by bi, this is equals to k. That means one is multiple to the other for all I equals to 1 to up to n, then again the equality occurs. So these are the two cases where the equality occurs. But the thing is, you need to recall. So here the case is k must be a non-zero real number. You need to recall this inequality, and obviously you will solve the problem. The problem is basically problem to find the least and greatest value of the function, say f(xy) equals to x plus y multiple 1 minus xy by 1 plus x square multiple 1 plus y square. Or the question is like this: the least and greatest value of the function x plus y multiple 1 minus xy by 1 plus x square multiple 1 plus y square are respectively option A minus half half, option B minus 1/4, option C 1/4, 1/8, and option D minus half and 1/8. So these are the four options. The question is given either in one option correct form or maybe as a question paper. So here we just apply the Cauchy-Schwarz inequality, and the Cauchy-Schwarz inequality, in that case we need to choose A1, A2, B1, B2, and we apply. So as per example, I have just for the solution, we take A1 equals to 2x and A2 equals to 1 minus x square, 1 minus x square. Obviously, these are real number for all xy. And we choose B1 equals to 2y and B2 equals to 1 minus y square. Now we apply. So applying Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. So this will be 2x whole square plus a1 square plus a2 square, so 1 minus x whole square, multiple 2y square plus one minus y square whole square. This value will be less than equal. This value will be greater than equal 2x into 1 minus y square a1 a2. So just here this will take b2 and this will take b1. So on this 2x into 1 minus y square a1 a2, a1 b1 and a2 b2. So a2 b2 2y multiple 1 minus x square whole square. So by using the Cauchy-Schwarz inequality, we'll write this thing. So just we'll do the basic calculation. So this implies 2 into x plus y into 1 minus xy whole square. This is less than equals to 1 plus x square whole square into 1 plus y square whole square. So that means this will be x plus y into 1 minus xy by 1 plus x square multiple 1 plus y square, that whole square less than equals to 1 by 4. Another thing is, say alpha square, we just recall this result. If alpha square less than equals to some lambda, so from this we can write mod alpha less than equals to root lambda. So obviously here we can write minus half less than equals to x plus y 1 minus xy by 1 plus x square multiple 1 plus y square less than equals to half, because here you can write minus root lambda less than equals to alpha less than equals to root lambda. So obviously here you just see this expression holds for all xy. So obviously the least value is minus half, and the greatest value and the greatest value is half. Now we'll try to know another important theorem. This is basically important theorem in inequality. What is the theorem? If a1, a2 dot an be n positive real numbers, they are all positive real numbers, not all equal. Not all equal. And pq are rational number. Pq belongs to q. The rational numbers, then inequality is a1 to the power p plus q plus a2 to the power p plus q plus dot dot an to the power p plus q by n. This value greater than or less than a1 to the power p plus a2 to the power p plus dot dot n to the power p by n multiple a1 to the power q plus a2 to the power q plus dot dot n to the power q by n. According as p and q have the same sign, p and q have the same sign. What does exactly mean? If p and q are the same sign, the greater than equality will hold. Or if they are opposite sign, then the less than inequality will hold. P and q are opposite sign. So based on this inequality, one problem is very, very important. The important problem is question number 6. If A, B, C, D all are positive real number, not all equal. Not all equal. So prove that A plus B plus C plus D multiple 1 by A plus 1 by B plus 1 by C plus 1 by D, that value strictly greater than 60. So in the previous case, this answer will be correct. Option A, and all other options will be false. Here the question is asked in similar way. One option correct question. Different examination. The question is like that. Let A, B, C, D all are positive real numbers, not all equal, then the least value of the expression A plus B plus C plus D multiple A to the power minus 1, B to the power minus 1, C to the power minus 1, D to the power minus 1 is option A 2, option B 4, option C 8, and option D 16. So obviously just you see the question paper and we have to prove that this is greater than 16. If you recall the statement, you can strike out the option. But you need to recall the statement. Otherwise you can't do it. So you need to solve. So how we will solve? So what should be the solution of this question paper? Just we apply the previous inequality. We will take p equals to 1 and q equals to minus 1. Just to see the power, we can consider is a to the power 1 plus b to the power 1 plus c to the power 1 plus d to the power 1. So here 1, 1, 1, 1. So I just consider p equals to 1, q equals to minus 1. That means p and q are opposite sign. If p and q are opposite sign, then the less than equality will holds, because in the inequality it is given greater than they have the same sign, and less than they have the opposite sign. Less than they have the opposite. So they have the opposite sign. So the inequality will be a to the power p plus q, that means 1 minus 1, plus b to the power 1 minus 1, c to the power 1 minus 1, plus d to the power 1 minus 1 by 4. Because it is opposite sign, this is less than a to the power 1, b to the power 1, c to the power 1, d to the power 1 by 4 multiple a to the power minus 1, b to the power minus, c to the power minus 1, d to the power minus 1 by 4. So it will be a plus b plus c plus d multiple 1 by a plus 1 by b plus 1 by c plus 1 by d. That value is greater than 1 by 16. So it will be just 16. Because this is 4 by 4, it will be 1. It will be 1. So greater than 16. So thus we can conclude our conclusion. The least value of a plus b plus c plus d, a to the power minus 1, b to the power minus, c to the power minus, c to the power minus 1 is 16. So this option is correct.